Okay, so even though a couple of you reminded me and asked me about if I was recording or not Friday in class, I was not. So, well, I thought I was, and I didn't check, and I wasn't. So I'm still gonna make the video for you here, reproducing Friday's class. 'Cause it's super important. It's a constant rate of change. It's a bedrock principle in all of calculus, and we really have to understand it well. So we started with this example in class of you and your dog painting a room together, and we said X was the total number of square feet that you have painted, and Y was the total number of square feet that your dog has painted. And the first question was, what is the distinction between X and dx? So X is the total number of square feet that you have painted. So what would dx be? So the differential dx means the change in X. So a change in X. In this case, X is the total number of square feet you've painted, so it's the change in the total number of square feet that you've painted. Okay, so then I turned the, and we also said that that would be calculated, you could find that dx by the final value of X minus the initial value of X. And that would be one way to calculate a change in X. Okay, so I turned the animation on, and in class, you looked at these questions. What is the animation showing? Be as specific as you can. So what it's showing is values of dy and dx. Notice what it's not showing is values of y and x. So this is showing a change in the amount that your dog has painted and the change in the amount that you have painted. And one question I asked was, are dx and dy, are those constant values or are those variables? Well, clearly what we're showing in this animation here is that those are varying quantities. dx here is shown to be increasing in magnitude, and for any given value of dx, dy has a corresponding value, and then those are increasing as well. So dx and dy are new variables that come from the quantity or the variables x and y. So this is showing that your dog paints more than you. And if I show this other view, we can see explicitly how the additional amount painted, or the change in the amount painted by your dog, is always 3 times as much as the change in the amount you paint. And so we could write that as dy equals 3 dx. And then the question is, does y change at a constant rate with respect to x? And the answer is absolutely, because for constant rate of change to exist, you must have proportionality in the changes of the quantities. Proportionality in the changes of the quantities. And that's exactly what we have. We have that dy is always 3 times dx. So yes, we do have constant rate of change of y with respect to x, and that's because the change in y is proportional to the change in x. In this case, the change in y is always 3 times the change in x. The additional amount that your dog paints is always 3 times as much as the additional amount that you paint, and that's what's required to say that y and x are in a constant rate of change relationship. Okay, and what is the value of the constant rate of change? Well, it's this value right here. It's the constant rate of change. And in this case, it would be 3 square feet per square foot. because for every square foot that you paint, your dog paints 3 square feet. For every additional square foot that you paint, your dog paints an additional 3 square foot. So that's why the units would be square feet per square foot. Okay, so then I moved on to a new scenario, and we looked at you and your friend painting your apartment. And so now you and your friend are painting a room in your apartment together. Let X be the total number of square feet you have painted, and let Y be the total number of square feet your friend has painted. And I said, let's show this animation. Now, how is this animation different? Well, for one, this now is showing the total amount painted. The previous animation showed corresponding values of changes in amount painted. Now we're showing the total amount painted. So if I could freeze this here at the beginning, it's showing that when this situation starts, you have painted less, maybe a half or a third of what your friend has painted. But then as you start painting together, you overtake your friend in total amount painted. So the question is the total number of square feet, does Y change at a constant rate with respect to X? And so we look at this and we say, oh, well, at first, X is less than Y. Then at some point later, looks like you and your friend have painted the same amount. And then later on, now you've painted more. So we clearly don't have proportionality of the amounts painted, the total amount painted. The amount your friends painted is not proportional to the amount that you've painted. But we have to remember that that's not the criteria for constant rate of change. The criteria for constant rate of change is proportionality of the changes in the two quantities, not proportionality of the quantities themselves. So it seems just from this view that the jury is still out. Even though the amount your friend painted is not proportional to the amount that you've painted, is it possible that the change in the amount your friend has painted is proportional to the change in the amount that you've painted? So I continued to alter this animation to help you maybe see that. And the first thing I did was I split up the bars into this black portion, which is kind of an initial amount that each has painted, and now this gold or orange portion of the bar is showing the amount of change, the additional amount painted from the starting amount. Okay, and if we were to analyze this in terms of constant rate of change, we'd be focusing on the orange parts of these bars, not the total lengths of the bars, but the orange parts. Is the amount, this change in Y, this orange length, is it a constant multiple of, or is it proportional to this change in the amount painted here? Okay, so we can illustrate those changes as dy and dx, and then I continued to alter the animation to help us compare dy and dx to see if they're proportional or not. So I moved back your friend's bar. So now we can compare with it. We can compare dy and dx here by lining up their left sides and see that it looks like dy is always 1/2 of dx. And that is indeed the case here. That the change in the amount your friend paints is always half of the change in the amount that you paint. So, constant rate of change. With a constant rate of 1/2 square feet per foot, per square foot. Square feet that your friend paints per square foot that you paint. So for every additional square foot that you paint, your friend paints half a square foot. So if you paint an additional 40 square feet, your friend just painted an additional 20 square feet. So this is constant rate of change, again, because constant rate of change between two quantities y and x is about having proportionality of the changes in the quantities, or in other words, dy is a constant multiple of dx. Okay, so to further bring home this point that this is a constant rate of change relationship, I showed you another version of these two quantities changing together. So this is just another version of these exact same two bars. The way that they're changing together is exactly the same. So remember that the starting value, you painted about 1/3 as much as your friend to start. Right about there, it's starting at 1/3, but then at one point you've painted the same total amount, and then you overtake your friend in terms of total amount painted. So this is the same mathematical situation in terms of the bars. And what we said was, we could take your friend's bar and rotate it so that stick it on the end of your bar. And now the lengths of the bars are still in the same animation as before. You start out painting about 1/3 as much as your friend, but then at some point you've painted the same amount, and then you overtake your friend so that x is greater than y. So everything, all the mathematics is the same, we've just changed the location of this bar. So now if we would plot every point of x, or every correspondence point of amount that you've painted and amount that your friend has painted, and then that locus of points, get ready for it, here we go. Then all of those correspondence points between a total number that you've painted, square feet, and the total number of square feet that your friend has painted, all those points would fall along a straight line. Again, reinforcing that we have constant rate of change. Even though we don't have the proportionality of the quantities, we have the proportionality of the changes in the quantities. Okay, so let's let x be any value here. So I'm just going to freeze at any particular value. We don't know what it is. So we're not interested in what that value is. And we know, and I'll tell you that initially, at this point where you have painted 50 square feet and your friend has painted 150 square feet. Okay, and so what we have here is then we can call this some arbitrary point on the line, and we can call it xy then to mean any point on the line. It could have been this one, it could be this one, it could be this one, it could be one that we haven't shown yet. Any one of these points on the line can be this xy, and therefore it represents every point on the line. So we want to take a look at, starting at our initial correspondence point of 50 square feet that you've painted, 150 square feet that your friend has painted, and this final correspondence point of any amount that you've painted x and the corresponding amount that your friend has painted y. What would dx be in this situation? Well, it'd be the change in x starting at 50 and ending at x. What would that change be? Well, it would be x minus 50. And then what would the corresponding change in y be? Well, we said that since it's constant rate of change, that in your friend, the additional amount your friend paints is always 1/2 of the additional amount or the change in the amount that you paint. So dy would be 1/2 dx, and in this case, then it'd be 1/2 x minus 50. Okay, and then the question is, what is this corresponding value of y to our starting value, to our value of x that we started with here as the final value of x? And so, well, so y would simply be what your friend had started painting at, a total amount of 150 square feet, plus the change in how much. Oh, this should be 1/2. I have it right here, but I didn't write it right here. So the 150 is the initial amount that your friend started painting plus the change. Would give the new final amount that your friend had painted. Total. So what did we just do? We just wrote the equation of the line. This equation generates any value of y given any value of x. And so it's the equation of the relationship between x and y. So given a final total amount that you've painted, this will generate the corresponding amount that your friend has painted. And so, just as an example, in blue here, suppose that you've painted 850 square feet. So by substituting 850 into this equation and solving it, it goes through this process that we just did. So by putting 850 in for here, for x, the first thing that you do, that the equation does, is it subtracts 50. What does that represent? 850 minus 50. Well, that's final amount painted minus initial amount painted. So that's showing us that our dx is 800 square feet. Our change in x. And then what does this do? Well, we know that the change in the amount your friend has painted is always 1/2 of the change in the amount you painted. So dy then is going to be 1/2 of that. So 1/2 of this 800 square feet is 400. And then that additional amount painted by your friend, the 400, then you would add to how much your friend had painted before to get the new total amount painted by your friend. So then y, this way, y would be the 150 plus the 400, which would equal 550 square feet. Which would be the correspondence to that would correspond to the total amount that you've painted of 850. So when you reach the amount of 850, your friend has reached the amount of 550. And this process of dx is the change in x, and then dy is going to be our constant multiple times the change in x. And then we're going to take that change in y, we're going to add it to the starting value of y, or the initial y, to get the final value of y. And so now we have a correspondence point. So maybe that point is who knows, maybe that point is right here, signifying that when you've painted 850 square feet, your friend is up to 550 square feet of total amount painted. So the equation is reflecting, this computation here is reflecting the change in x, then next the change in y, added to the original y gives the new value of y. And then you have a correspondence point of the final value of x and the final value of y, 850, 550 square feet. Okay, so we moved on to a new scenario then. Let's take a look. Working on a constant rate of change here. And we said that suppose you open your laptop during class to take notes, and 35 minutes after class started, your laptop battery has a 41% charge. 75 minutes after your class has started, the battery has a 28% charge. Percentage charge P changes at a constant rate with respect to the number of minutes since class began. We'll call that T. So without doing any calculations, what are our units of M, the constant rate of change? So the constant rate of change of percent charge with respect to number of minutes since class began. So that those units would be, well, if it's percent change per unit of time, then it's going to be percent per minute. And then how can you interpret, so that will be some number. How can you interpret the meaning of that value? That value is going to be the change in percent that occurs every minute. Okay? M is measured in percent per minute, and its value is the percent change of the battery in every minute of time. Okay? What is the value of dt according to the information given? So the final value of time of t was 75, and the initial value was 35, so we could say dt is 75 minus 35, or 40 minutes. So then we have a 40-minute span of time here, that's our dt, and remember that dt is a variable. dt is a variable, so we're not, this is a particular dt that we're looking at in this scenario, but dt varies. dt can be 1 minute, 2 minutes, 5 minutes, 6 minutes. Okay, so right now we're looking at this 40 minutes. So then what would 1/40th be? So 1/40th would represent 1 minute. It would represent 1 minute. So 1 minute is 1/40th of 40 minutes. So that's the fraction of time that 1 minute is to 40 minutes. In other words, 1 minute is 1/40th of 40 minutes. Okay, and we're going somewhere with this. There's a reason I'm asking this question, so we'll hold on to that thought. So what value of dp corresponds to this change in time? And I should have minutes. Okay, so what value of dp corresponds to a dt of 40 minutes? Well, as the time changes from 35, t changes from 35 to 75, the charge changes from 41 to 28. So our final value is 28, our initial value is 41. The change in P is negative 13%, or a decrease in the battery's percent of 13. So we have the change in time is 40, we have the change in the battery is negative 13, and so the constant rate of change, yes, it would be dp divided by dt, but we want to use this fact to really understand why that's true. Why is it dp divided by dt? So remember that 1/40th is the fraction of time that 1 minute is to 40 minutes. And so we ask this question. If the battery percentage changes negative 13% in 40 minutes, and 1 minute is 1/40th of 40 minutes, then how much does the battery percentage change in 1 minute? So if it changes this much in 40 minutes, then how much will it change in 1 minute if 1 minute is 1/40th of 40 minutes? Well, we're taking 1/40th of 40 minutes, so we need to also take 1/40th of negative 13%, which would be multiplication. 1/40th times negative 13, which would give a value of negative 0.325% per minute. And so this right here, if it changes, again, if it changes negative 13% in 40 minutes, we want to know how much changes in 1 minute. Well, that's 1/40th of 40 minutes, so we're going to take 1/40th of negative 13%. And that's that calculation right there. And that is why m is dp divided by dt, because this is our dp, and this is our dt. and we're by taking 1/40 of negative 13, that's equivalent to negative 13 divided by 40. And that gives us this value of negative 0.325% per minute. Okay, so looking at this initial correspondence point of 35 minutes and the 41% charge, let's develop the equation of this line and take a look at, so let's kind of analyze the situation for an increasing amount of time and the corresponding decreasing charge in the laptop. So let's open up a new GC window. And let's just write down. So not only does this mean that every minute the charge changes by negative 0.325%, but more generally than that, and really, really important for constant rate of change, is that given any amount of time, any change in the amount of time, dt, the corresponding change in the battery charge will be negative 0.325 times the change in t. So if 2 minutes go by, then 2 times this much percent will be the change in the battery percentage. If 10 minutes go by, then the percent charge in the battery will change by negative 3.25%. So given any change in t, this number tells us this is a constant multiple of that change in t that will give us the corresponding change in p, or percentage of the battery. Okay, so we have this graph here, and I want to plot this correspondence point of 35 minutes and 41% the battery is at. So I'm going to graph that right there. So we got 35 and 41, and we know that's a time in minutes, and that's our percent. This is our percent here, and this is our minutes. Minutes since the beginning of class. And okay, so suppose we want to use this information then. We've found our constant rate of change. And we want to use this information to find what's the percent in the battery when 60 minutes, we're into class 60 minutes. I'm just gonna, I don't know what it is, but I'm just gonna guess it's right here. So here we are, 60 minutes into class. What's the corresponding percentage of the battery that remains on the laptop? Well, we can first start by, we know that we started at 35 minutes, we ended at 60 minutes, so we can first find the change in time. And that change in time will be 60 minus 35, or 25 minutes. And again, what does this value tell us? This constant rate of change tells us that any change in battery life is always negative 0.325 times the change in time that goes by. So we have a change in time of 25. Therefore, we immediately know what percent the battery has changed, because we have constant rate of change, and the percent change of the battery is always negative 0.235 times the change in the time that we have. So this would tell us that dP is negative 0.325 times our 25. We can just come up here and do that. So negative 8.125. And that will be represented by this decrease right here on the graph. So the change in P is going to be M times the change in T, negative 8.125%. So what's the new percent change of the battery? Well, at 35 minutes it was 41, and then as the time changed from 35 to 60, the percent went down 8.125%. So this P is going to be that starting value of percent, 41, plus the change, or minus 8.125, which will be, so I can just change I know this is my change, so I'm just going to add 41 to that. So 41 minus our change of negative, or 8.125, 32.875. So we have a new correspondence point of 60 minutes and 32.875% charge of the battery remaining. Is that correspondence point right there. Okay, so let's do one more thing. Start over with that point right there. And now let's let, what did we have? We had 60 and 30, just so I can get an idea of where this is going to. So just to get a sketch of all the points. And so just arbitrarily pick this point right here to be every point T and P, starting at our initial point of 35.41. We realize a change of T of a dt of T minus 35, a corresponding dP of always, dP is always negative 0.325 dt, meaning our final P is the initial P 41 plus the change in, oh, so I didn't write what the change T was, so negative 0.325 dt, which is T minus 35. So we have 41 plus negative 0.325. And so this represents all correspondence points. All correspondence points of time since class started and percent charge of the battery. So if I come over here and make a new command line and say y equals, so remember to graph, well, let's define the function. Let's define the function. So we're going to define the function p, control, and we don't want to use lowercase t, so I'll just use uppercase t, equals 41 minus 0.325 times t minus 35, and if I hit graph, it should graph it. Okay, it didn't graph it. Why not? Shouldn't that graph the function? No, because GC needs the prompt from us, either y and or x, to prompt that we want to graph something. So how are we going to graph this function? We're going to say y equals, we want all the values of the dependent variable. So we want all the values of percent change for every x that we plot. So we want to tell it for all x's on the x-axis, we want y to be all the corresponding values of the dependent variable p. So what do I want? I want p of x, and then we're going to start from x equals 35 because we don't know what happened before that. Less than x and less than, so the end of class was 75, so let's just show it from 35 to the end of class, and if we hit graph, there is our line. Let's make it a better color. So there's red. And so this was a sketch, this was a guess at where the line would fall. But so now what do we graph? We've graphed all the correspondence points, which are determined by all the values, the corresponding values that would make this equation true. Given a time t, the corresponding percent of the charge in the battery is each one of these points of the graph.